Um, Jacob, the laws of physics, historically, not to be a historian about it, is quite an interesting term. In the old medieval period, perhaps you would say under the more religious context, laws were given by God. They governed the universe, they governed space and time before, obviously, we had space and time in an Einsteinian sense. But laws were essentially quite theological. They governed existence and properties of space and time. Descartes also discusses as well with more of a nuance of mathematics and religion. In the contemporary world, we've moved on somewhat. We've got great laws of physics in terms of, obviously, we've got Newtonian laws of motion. Space-time is not actually a law from Einstein, it's more of a theory. But this is all to say that the way the contemporary world uses and employs laws is different from its theological underpinning. So now we just take laws as principles that may govern or regulate states, but we tend to drop the religious angle. But people still use laws. Someone being so well versed in the philosophy of physics and cosmology, I just want to get as a starting point how you think about the laws of physics and what they are and what they do.
It's an excellent question. I like to exercise a significant amount of humility around that question. I honestly don't know. So one view, and I'm assuming people who've listened to your interviews before are probably well versed in this, but yeah, some of your listeners may not be. So if it's all right, let me summarize a little bit.
Of course.
Very broadly speaking, and this course grains over quite a few other nuanced positions, but broadly speaking, the two dominant views on laws of nature are the so-called Humean view. Yeah, and I think Barry Lower, exemplifies this view quite beautifully. This is a view that the name Hume, David Hume, is attached to it, but it's a 20th century innovation. And the idea is that laws are not these extra physical entities that exist outside the universe and reach down and dictate what happens in this quasi-theological sense, but laws are summaries. They are summaries of the patterns and phenomena that we observe, that we find empirically in the natural world. The patterns are primary. The patterns and the phenomena are what are really out there. And we come up with laws to summarize, to explain, to describe, to compress the information contained in those patterns into relatively simple, easy to understand principles and rules, the rules of the universe. And so the laws don't have their own status as metaphysical entities separate from the phenomena. And there are some good arguments for this, right? One argument is, well, if there were these laws outside the universe, somehow governing or dictating phenomena, how do they do this? What is the mechanism by which they do this? The other view, the so-called primitivist view, is that laws are primitive features of reality. They exist in some sense over and above the phenomena in nature, and they govern. They dictate what happens in some sense. And there are different ways to think about how laws can dictate. A very traditional way is to say that the universe progresses from moment to moment, and the laws dictate the next moment based on the previous moment. This is the so-called dynamically productive view on how primitivist laws govern. There's I think a very interesting, I would argue, somewhat more, potentially more modern view. And this view has been pushed, I think, quite wonderfully by people like Emily Adlam, and also Eddie Chen and Shelley Goldstein. And the idea here is that laws don't necessarily act in a dynamically productive way from one moment to the next, but they constrain phenomena in a kind of global sense across all of space and time. And one reason to generalize how we think about laws in that way is that there do appear to be some laws that just don't neatly fit into the dynamically productive paradigm. Here I'm talking about things like conservation laws. I'm also talking about various constraints that can show up in various laws of physics, and even equations like the Einstein field equation that describe how matter and energy are related to the shape of space-time and the interplay between matter and gravity. The Einstein field equation does not, in general, take the form of a dynamically productive law. You can recast it in that form in certain circumstances, but as a broad statement, it doesn't always neatly fit into that mold. Now, there are, of course, ongoing disputes about the status of the Einstein field equation as a law of physics. You only have to read anything that Eric Curiel has written about this. So there's dispute over exactly what's going on with these laws. Nonetheless, there is some argument for trying to think a little bit more broadly about what a primitivist law can look like. However, what a Humean about laws might say to the primitivist is, well, whatever your sense of laws, primitivist, how do you explain how these laws reach down into the world and act? This does seem a little bit theological, like you've gotten rid of certain aspects of a deity, but you've retained its divine influence on the patterns of nature. And, this debate has been raging for a very long time. You'll hear sometimes a primitivist say, well, we mean it in the same sense that, you look at a sheet of paper printed out by a computer, and that sheet of paper has patterns on it. And if someone shows you a sheet of paper with a bunch of letters and shapes and patterns on it, you would ask, what are the rules that generated that sheet of paper? And that's what we mean by the laws of physics. Otherwise, the patterns on the sheet of paper have no explanation at all. And then, of course, the Humeans will say, well, but that's not the same thing, because in the case of a computer, we actually can understand how the rules end up turning into the shapes and the symbols on the paper. We can tell a complete story. We can understand how the rules were encoded in the computer. And if we have the time and we're willing to put the thought and effort in, we can track exactly, how the electrons move through the logic gates and how the wires connect and how eventually you end up with the printer as a mechanism producing these patterns. So that's actually fine. The problem with primitivist laws is that we have no such mechanism. And then, of course, the primitives will say, well, then how do you explain the patterns? There are all these patterns and phenomena. You're just saying that they're inexplicable. And the Humeans will say something like, well, you're not helping because you're replacing one mystery with another. You're asking us where the patterns come from. We could just as well ask, well, where do the laws come from? And how do the laws act on the patterns? In fact, you've got two mysteries instead of one. And this debate has been raging forever. I mean, if you ever sit in a seminar with Barry and Tim Maudlin, they'll just go back and forth, and they've been doing this, as far as I can tell, for their whole careers. So what is my view? I actually don't have a strong view on this. I would say that it's not that I think that one view is necessarily correct. I think there's an advantage to thinking flexibly about laws. Sometimes when I'm thinking about a given model or theory, I find it helpful to think about laws in a Humean summary sense. And sometimes I find it more useful to think about laws in a governing sense. And I think being flexible about how you think about things is not a bad thing, but a good thing. So, and in some ways, I see some of the work that I've been doing as, well, let me say it this way. There have been some arguments over the years that modern physics has made the Humean view less tenable. The most, comprehensively stated Humean view, up until somewhat recently. I mean, Barry has this extremely interesting package deal account of Humean laws, but before that, I would say the most well-developed sort of picture was the Humean supervenience picture of David Lewis, 20th century metaphysician, who said that in his view, phenomena, the universe, was just a collection of patterns, of local happenings, with no fundamental connections, no sort of modal structure, no cause and effect connections, no law-like connections, just phenomena happening. And the metaphor he gave was that there was this mosaic, the Humean mosaic, which was just this set of all points in space-time. And at every point in space-time, things could happen or not happen. And there were patterns in this mosaic, just like an actual mosaic. You look at it and see patterns in it. And if you wanted to describe this mosaic to somebody else, if you wanted to predict what you would see beyond the parts of the mosaic to which you had epistemic or empirical access, Or if you could see a lot of the mosaic, but it was just really complicated and you want to give a concise summary, then you would talk about laws. You would talk
Yeah.
about laws as a way of summarizing what you were seeing in the mosaic. And there have been arguments, I think, ever since people began taking things like entanglement seriously in quantum mechanics, that entanglement being this sort of spatially non-local, but at least non-separable, spatially non-separable phenomenon, made it untenable to think that you could just have a mosaic with isolated goings about. That
Yeah.
there was something holistic about the ontology of quantum mechanics that presented an obstruction to this Humean supervenience picture with the Humean mosaic and then these sort of laws as summaries describing what was going on. The project I'm working on, I think, opens the door again to a Humean supervenience type picture. Do I think it makes Humean supervenience the canonical picture of the universe and how the laws of physics work? No. But I think it makes the world safe again for those who want to take that point of view, whether the sort of original Humean supervenience account of David Lewis or the somewhat more modern versions of it, like Barry Lower's package deal account. I like to be pluralist about how I think about metaphysics and the laws of nature, because, like I said, thinking flexibly about the features of how we think about the universe serves us well in formulating new ideas and new physical theories. So I think to the extent that what I'm trying to do is open up space for people to think flexibly again about metaphysics, I think that's part of where I think there's progress here.
Obviously, David Lewis is so well known in this space, and so is Humean supervenience as well. I'll make a remark about that in a second. But in terms of going back, in terms of this issue about dynamical laws, that's very important. I know you mentioned Emily Adlam as well, and Eddie Chen's. I won't get into the actual ontological existence of the wave function. I may do a bit later. But Eddie Chen's also a person doing a lot of work in laws of physics as well. But taking a step back in terms of dynamical laws, obviously that's why Tim Morden's got elements of his float. But going before Lewis, another contemporary in that era was obviously Armstrong. And I like Armstrong's view of the laws. Obviously, it's problematic for dynamical laws as well, which you would have noticed. There's always an issue of what you can do with dynamical laws as well. Obviously, you referenced there some elements about, in terms of Lewis, whether the laws are just patterns that just can or cannot create the next stage, so to speak, in a time sequence. Obviously, that's going to have issues for determinism, which is a separate issue that I won't cover here. But I think what's interesting to note in terms of primitivism, which is, I like the way you summarized it there. The thing I'm attracted to about the human view of it, so the Lewis bit is very useful, very interesting. I do think, though, with that problem with the Humean pattern is, if it's just regularities, because obviously it comes from inductive logic from David Hume. If it is just regularities and there's no such thing as cause formally, then there is an issue there of what it is that the laws are doing if they can't necessitate elements. So if they're just regularities, could they actually cause anything? Can they actually make anything move? So that's, for me, personally, limitation of the Lewis account of it. But what I do like about the humans, and feel free to chime in on anything when you want. What I do like about the human stuff that they've got over the primitivists is that they avoid that potential infinite regress that we discussed briefly over email exchange that I sent you in terms of bits of this agenda. Is they avoid that metaphysical necessity, as Paul Davies says, well, where do the laws come from? So if you're a Humean and you're like, I don't want it to be a primitive because the primitive has to tell me why these laws are the way they are, where they come from and why they exist. Where humans, like, we don't worry about that. They're just in the empirical world, and we may do obviously theories that can explain or combine observed patterns of regularities. We don't worry about the primitivists as elements of it. The primitives can obviously have some attacks on the human views of it, like I've just had in terms of irregularities. But at least the primitive at a superficial level has an issue of, well, where do these laws metaphysically come from? And as you alluded to there are hang-ups and hangover from the philological aspect of it. So I think the Humean element, for me personally, you can get more legs out of it in terms of, well, you don't have to necessarily say, well, why are the laws of physics up here and why are they the way they are? Is it necessity? It could have been something else. And obviously, Paul David speaks a lot about that as well. But so that's just one view of it. The primitivists are quite interesting in themselves. But what I wanted you to get as a speaker before you want to address anything from your papers as well in terms of quantum mechanics is a very interesting point you made where in terms of entanglement has changed our perspective on how we think about laws if people take entanglement and quantum mechanics very seriously. So, but I just wanted to get your first perspective on for example, Eddie Chen's already got a piece out on the ontology of the wave function, whether the wave function actually exists. But before we address that, I just want to get your perspective on if we're looking at quantum mechanics and the measurement problem and the wave function, in terms of the interpretations of quantum mechanics, from your perspective, how would you address the problem? So Niels Bohr's obviously was the instrumentalist view of quantum mechanics. So is there an issue with quantum mechanics and the laws of physics if you just think that quantum mechanics isn't ontologically real? And Roger Penrose has got a view about this as well. It's like, this can't be actually true. This can't actually be serious because look at it, it's ridiculous. And Niels Bohr is like, well, it's a mathematical formula and it's instrumentalist and it works and it's got stupendously good predictive power, but it might not actually really exist. It's just an instrumentalist account, possibly an anti-realist account. How do you feel about that, whether that's actually viably true or not? And how do you think that relates to any kind of laws in physics?
Pinning down Niels Bohr's precise interpretational views on quantum mechanics is a difficult task. It's a difficult task. If it were a function, it would be an uncomputable function. So I don't know whether I would put Niels Bohr exactly in the instrumentalist school about quantum mechanics. It's kind of hard to say exactly what his views were. But let me say, I mean, there's so many interesting points you raised. I'm trying to make sure I address all of them because they're all very interesting. So let me step back a little bit and just talk a little bit about what I think is wrong with quantum mechanics.
Please do. Go ahead. Yes.
And when I say what's wrong with quantum mechanics, I'm not attacking like the theory, and I'm not saying that quantum mechanics is empirically incorrect. I'm not saying any of that. I mean something a little more specific. When you pick up a textbook on quantum mechanics, and here I'm talking about any of the standard textbooks that a physics undergraduate student is likely to encounter in coursework. David Griffiths's book, Introduction to Quantum Mechanics, Sakurai's book, Modern Quantum Mechanics, Shankar's book, Principles of Quantum Mechanics, Townsend's book, also these Modern Introduction to Quantum Mechanics. They're all interesting and good books. Like, they're great pedagogical books. But the way they lay out the theory, the axioms that they provide, roughly speaking, work in the following way. These are the axioms. You can break them up into different ways. I think of them as 5 axioms. And the basic problem with the axioms is that they're either incomplete or they're inconsistent, or maybe both. And there are several problems with the axioms. The most well-known one is the famous measurement problem. The axioms invoke the notion of a measurement, measurements of observables, in a crucial way without defining what a measurement is, without defining what kind of process, what kind of physical process constitutes a measurement. The axioms take a measurement as a primitive. And this is bonkers because a measurement is clearly not a primitive feature of fundamental reality. A measurement is done with an apparatus made of screws and optics elements and lasers and machines of various kinds. I don't think machines that sit on tabletops or that are part of giant particle accelerators are part of the fundamental structure of reality. Basically, what the measurement problem is that the axioms depend in a very crucial way on this ill-defined concept of a measurement.
Yeah.
That's the measurement problem. And that's in the short answer of what the measurement problem is. I can go into more detail about it. And there's been this attitude that's developed in physics over the century or so since the dawn of quantum mechanics, that this is how science was always supposed to be, that thinking about science as anything other than a set of instrumentalist tools for relating preparations to measurement outcome predictions was always naive. And one of the things that quantum mechanics did was it made us more mature about science. It made us realize that science was never about talking in terms of phenomena happening in the world. The proper way to think about science was relating preparations to predictions of measurement outcomes through a mathematical model, and that's it. That's all science is.
Mm.
Now, and some people regard that as a form of intellectual progress. I do not, for a whole variety of reasons that we can talk about. So one attitude is just measurements can be primitives of a physical theory because this is what physical theories are supposed to do. They're supposed to relate preparations to predictions of measurement outcomes. And so what else could you ask for? I think explaining why the measurement problem is in fact a problem requires a little more detail. And I think there's no easy way to avoid just talking about the axioms, listing them, saying what they are so that we have them on the table and we're in agreement. You pick up any of these textbooks on quantum mechanics, and roughly speaking, here is what the axiomatic basis for the theory is according to these books. Axiom 1 says that when you want to model or describe or formulate a system according to the rules of quantum theory, you're supposed to introduce a kind of a space called a Hilbert space.
Yeah.
This is not physical three-dimensional space. It's not configuration space, which is the set of possible configurations a classical system could have. It's not that. A Hilbert space is a very abstract space. It is a kind of vector space. Vector space here just means the elements of this set or space are mathematical constructs that can be added to each other, that can be rescaled by multiplying by numbers. Roughly speaking, that's what a vector space is. The simplest example of vector space is the set of arrows in three-dimensional space, and there are rules for putting arrows together. This Hilbert space that we're talking about is not generally visualizable in that way. For one thing, it's not visualizable because although some systems it may be low dimensional, for many systems it could be very high dimensional or even infinite dimensional, at least under some idealization process. So it's a vector space of some dimension. The dimension depends on the system that you're asking about. And it's also a vector space in which the numbers you're allowed to use are not just the real numbers, but the complex numbers. You're allowed to use real numbers as well as the imaginary unit, formally defined as the square root of -1. So you're allowed to multiply your elements of this vector space, your vectors, with complex numbers. There's also an inner product. It's like a dot product. If you've learned about vectors, there's a dot product. There's a rule for taking two vectors in this Hilbert space, combining them and getting a complex number. And in the cases in which this vector space is infinite dimensional, we put further conditions on it. We require that it be complete in the sense that this is now very technical, the Cauchy sequences converge to an element in the Hilbert space. And also the Hilbert space is separable, which means that it has at least some countable bases. Okay, that's all sort of like very technical stuff in the infinite dimensional case. So there's this Hilbert space. And what is the Hilbert space doing? What role is it playing? Axiom 1 says that to represent, in some sense, the state of your quantum system, you need to pick out an ingredient that is associated with this Hilbert space. In the most idealized simple case, the ingredient you pick out is a vector in this Hilbert space. The overall normalization of this vector turns out not to matter. Its length does not turn out to matter. So some people take the equivalence class of all vectors that only differ by length, and they call that a ray in the Hilbert space. Somewhat more generally, you can't always assign a state vector, a vector, or an array, or a ray to a state of a quantum system. More generally, you have to associate a linear operator on this Hilbert space called a density operator or density matrix. This is required in the somewhat more general case, when either there's some classical uncertainty involved or when your system is entangled with other systems. The best you can do is associate a density matrix with it. If you're lucky, or to some approximation, you can use a vector instead. That vector is sometimes also called a wave function.
Yeah.
So whether you're talking about a wave function or a density matrix, some element associated with this Hilbert space it must be picked out to represent the state of the system in some sense. That's axiom one. I should say, by the way, that some people use the word wave function very broadly to mean a vector in this Hilbert space. Some people mean it a little more precisely to refer to the collection of coefficients of a vector in some basis.
Yeah. So that.
But there's some nuance in these definitions. But I don't want to belabor this. The point is there is this abstract, potentially high-dimensional inner product space, the Hilbert space over the complex numbers, and an element of it is used to represent the state of your quantum system. That's axiom one. That's just axiom one. Axiom two is a statement about how this quantum state changes with time when the system is not being measured. When the system is not being measured, this state is supposed to evolve in time according to a linear operation called unitary time evolution. And when this unitary time evolution, which is describable in terms of a linear operator, a unitary operator acting on the quantum state and giving you the later quantum states, when this evolution is sufficiently smooth, when it has a property called strong continuity, then there's a theorem, Stone's theorem, which says that you can boil it down to a differential equation meaning an equation that tells you every infinitesimal moment by infinitesimal moment what is happening to the quantum state of the system. And the simplest version of this evolution law is the Schrodinger equation. And the time evolution can be reduced to the specification of a certain operator called the Hamiltonian, a self-adjoint operator on the Hilbert space. And this operator, once you know it, you can use it to predict the behavior of this quantum state. That's axiom two. So axiom one, again, is the Hilbert space's quantum states, and axiom two is unitary evolution, or in many cases, the Schrodinger equation, the time evolution. Those axioms don't say anything about the physical world that we recognize. They're all mathematical abstractions.
Yeah.
So you need something else to connect these mathematical abstractions to either the physical world in some broad sense, or at least to empirical predictions. And that's what the other axioms do, the so-called measurement axioms. And the measurement axioms, I like to think of them as three axioms. One is that every observable feature of a quantum system that you might want to go out and measure is represented by, in the narrowest case, another kind of an operator on the Hilbert space called a self-adjoint operator. You can describe measurements in somewhat broader terms, in terms of what are called positive operator valued measures, but they're still operators. They're operators that live on a Hilbert space. And at least if you're talking about a self-adjoint operator, and you ask, okay, well, if I make a measurement of this observable for my quantum system, what are the actual results I can get? You're not going to get an operator. An operator is not the answer. You get a number. You get a real number. And the real number you get is associated with this self-adjoint operator. It is going to be one of the eigenvalues of this operator. And there's a whole mathematics and linear algebra about the eigenvalues. But basically, operators of this kind, self-adjoint operators, are associated with a collection of numbers in a deep invariant sense. If the operator is self-adjoint, the numbers are guaranteed to all be real valued. And when you measure the system, you're guaranteed to get one of these eigenvalues, one of these numbers associated with this operator, real number, as the numerical result of your experiment. So that's axiom three. The next question is, okay, well, if I get one of those eigenvalues, with what probability will I get it? And axiom four is the Born rule. Axiom four is a precise mathematical formula that says, you go and measure this observable, here is the probability with which you will get the result. And the probability is given through a mathematical prescription that combines the quantum state of the system, represented as a state vector or a wave function, or more generally as a density matrix. It combines that with some feature of the self-adjoint operator in question. You do a mathematical operation, and out comes a measurement probability, a probability that you'll get that measurement outcome. And then the final axiom is the collapse axiom, that after the measurement has been done, the quantum state changes abruptly in such a way that, and this is crucial, it doesn't just change, it changes in such a way that a single outcome is singled out, at least approximately, so that if you measure the same observable again, very soon after, before you've given the system to evolve by the Schrodinger equation, then you are almost certainly to get exactly the same result you got before, right? But it's crucial to point out that the collapse axiom is not just a change in the quantum state, but it's a change that singles out a specific outcome, and the
Yes.
other ones go away.
Yeah.
That's how the collapse axiom works.
Yeah.
Now, I've tried to be very precise. You can see I'm trying to be very
Yes.
precise in
Yeah.
how I say all these axioms, because you need to be precise, because otherwise people goalpost shift. But I'm even leaving some things out, right? When I talked about quantum systems evolving unitarily, that's only for closed quantum systems. And if you
Yeah.
ask, what is a closed quantum system? Roughly speaking, it's a system that is well isolated from its environment, a system not being measured. But that's actually kind of complicated, because if you put a particle, in the presence of like an external potential, you can use the Schrodinger equation, but the potential is certainly coming from outside the particle. So there's some sense in which the particle is in fact interacting with what's outside of it. So what exactly is the precise sense in which a system is truly closed? If it obeys the Schrodinger equation. So it's sort of circular. Like
Yes.
closed systems obey the Schrodinger equation, and which systems obey the Schrodinger equation, by definition, those are the closed system. I mean, it's a little bit circular. But as best one can say, when your system is not exchanging interactions with its environment, that's when you can regard the system as being closed.
Thank you, Jacob. Excellent. For
So
first,
those are all the axioms. But let me just say, okay, so now that we've listed them, you'll notice that they invoke the notion of a measurement.
yeah.
You can see very clearly the three additional measurement axioms rely on this notion of a measurement, but they don't define what constitutes a measurement. And, one attitude here is, well, does it really matter? I mean, I can go out and use these axioms. I'll do a measurement. I can only obtain empirical data. I can only make observations through some kind of measurement. And these exactly tell me what's going to happen. So what's the problem? I think the problem was most sharply explained by Hugh Everett in his long form. He had a full dissertation, he had a full long form dissertation called The Theory of the Universal Wave Function. He wrote it in roughly 1956. He was a graduate student at Princeton, a student of John Wheeler, but also, I believe, Eugene Wigner was at Princeton at the time. And he introduced at the beginning of this long thesis. It's not in the short version that he ultimately had to publish. It's in the long, sort of unpublished version. At the very beginning, he introduces a thought experiment. This thought experiment, I think it's not widely known that it first appeared, as far as I know, in his thesis. It's it's more usually associated with Eugene Wigner. It's called the Wigner's friend thought experiment. Eugene Wigner introduced it in a paper. I think he called it On the Mind-Body Problem was the paper in the 60s. But as far as I know, it actually first appeared in the 50s in Hugh Everett's thesis. And it's very simple. It's an extremely simple problem. You have two observers. One is inside a sealed box, kind of like Schrodinger's cat, and the other is outside the sealed box. And the box is perfectly sealed. Now, this is not a feasible experiment with modern technology. We can't seal the interior of a macroscopic box from thermal radiation, from X-ray. We can't do this today. But this is a question of principle. One observer is inside the box. That's Wigner's friend. And Wigner is outside the box. Wigner's friend does a measurement on some quantum system inside the box. Wigner on the outside does not do any measurement. And now we have a problem. Wigner didn't do a measurement. Wigner's friend inside the box did. So do we apply the collapse axiom or not? And we have to take a stand on this question. We have to decide what we're going to do. One attitude is to say, well, I think a measurement was done, so we do have to collapse it. But in that case, the collapse is going to change the quantum state and alter the predictions that Wigner's friend, but also Wigner on the outside makes. Right? Because the collapse happens, you've altered the quantum state. Yep. And this will have downstream empirical implications for the predictions that Wigner on the outside of the box will make. Now, one attitude is maybe decoherence solves this problem. There's this process in quantum mechanics called decoherence that does not rely on the collapse postulate, that does change the quantum state. And I said before, the collapse postulate is not just about changing the quantum state, it's about singling out an outcome. The problem is decoherence does not single out an outcome. Decoherence does modify what the quantum state looks like, it rediagonalizes it in what's called the pointer basis, but not exactly. There are always small deviations that show up in decoherence. Collapse banishes them. Decoherence leaves these tiny, tiny, tiny effects in there. These are so-called coherences. And in principle, Wigner could tell the difference. Wigner, on the outside of the box, could empirically distinguish between true collapse and no collapse, but just decoherence, by doing a very elaborate interference experiment on the box. So now this experiment would require fantastical technology far beyond our present abilities. There's this wonderful theorem that Scott Aaronson proved called the quantum necromancy theorem that says that if you had the ability to do this experiment, it would be equivalent to the ability to raise the dead, to reverse what we think of as a thermodynamically irreversible phase transition from life to death, or unscramble eggs or things like this. So this is obviously fantastically difficult, but there is no in principle reason you could not do this. And so that means that there is an empirical difference, at least in principle, between just decoherence and collapse. And Wigner on the outside of the box could tell the difference between the two. So the question is, did a measurement really happen? Did collapse really happen? And if it did, then we can start asking all these questions. Well, the person on the inside of the box did the experiment. They caused collapse. What if the person in the box was replaced with a gerbil? What if the person in the box was replaced with an insect? What if the person in the box was replaced by a tardigrade, one of those microscopic water bears? What if the person in the box was replaced by a bacterium? Right? At some point, you have to ask, when does an outcome get singled out and get collapsed or not? And we run right into the measurement problem. We don't have a rigorous definition of what counts as a measurement. So either you have to supply that rigorous definition, and it's been 100 years and no one has a rigorous definition. So that's the measurement problem. That's one way out. Another way out is to say maybe there is a single outcome, yes. Maybe Wigner's friend does get a single outcome, but maybe there just isn't a collapse. Maybe we just throw away the collapse axiom. Somehow we both have a definite outcome that was obtained by Wigner's friend, but there was not, in fact, a collapse. Well, the moment you do this, you now have a hidden variable, because you've got a wave function, or more generally a density matrix, that does not single out a definite outcome, and yet there is a definite outcome. By definition, that means that there's more to reality than is reflected in the quantum state, and that's literally the statement that there are hidden variables. So that's option 2. You introduce hidden variables. And option 3 is to just deny that there was a single outcome at all, to say that no single outcome was obtained. And the only remotely well-defined view in which you deny that there was, in fact, a single outcome is something like the Everettian or many worlds view. Those appear to be your 3 options, right?
Yeah.
All of them require modifying the axioms of textbook quantum mechanics. All of them require confronting either the incompleteness or the inconsistency of the textbook axioms, and they require that you pick a direction. Now, I happen to think that we're not going to have a rigorous definition of a measurement. We haven't in 100 years, and it would be kind of amazing, again, if there were a rigorous definition of a measurement, the kind of stuff that we do on our tabletops or in public accelerators written into the fundamental laws of physics. It just seems like absurd. So that leaves us with the other 2 alternatives. Deny that there are, deny that the density matrix contains all the information and that there are above and beyond other variables, hidden variables that specify a unique outcome. That's option 2. And option 3 is something like a many worlds type ontology. Well, I happen to think there are some pretty serious problems with Everettian quantum mechanics. There are long-running questions about whether you can extract probabilities from the theory in a well-defined way. We can get into that. That would be a whole other conversation. But in any event, I have a lot of reasons to be very skeptical of that approach. And that basically leaves me with quantum mechanics is just incomplete. And we need to include something else, some other kinds of variables.
In terms of thinking about the different mathematical aspects and all the axioms involved in terms of the vector spaces as well. In axiom 1 as well is a different. I like your discussion about we don't actually have anything that constitutes a formal measure. And obviously, when we've got a measurement problem, that's obviously related to the mathematical problems you just highlighted there with the measurement as well. And obviously, we've got many worlds. We've got the hidden variables, one that you just alluded to as well. Many worlds, as Sean Carroll popularly espouses, the one that leaves, as you were describing there, all the mathematics as it is and doesn't require a hidden variable, doesn't require anything else. I don't know if, obviously, you just gave a very sophisticated, elaborate run through of the maths there. I don't know if you know James Reed at Oxford, who's a specialist in philosophy of physics as well. Without capturing all the elaborate maths that you highlighted there, a good way to simplistically think about what the problem is with the measurement problem is obviously just in terms of the mathematics behind quantum mechanics, which you just went into great detail into. But obviously, you can't know the position and the momentum, and it's a probability, and it should be either here or here. There's also an issue that we won't get into right now in terms of is it here and here, or is it here or here, separate issue. But it says probabilistically you can only know where it is here. So when you basically pull out a measurement, you're not meant to know whether it's here or here, but you measure it, and as you were saying, probabilistically in terms of the maths, it's actually here. That's generally a very simplified way of the measurement problem, and you've elaborated into how that's problematic in terms of the maths and hence all the interpretations behind it. I just want to pick up two things on that, if I can, from my perspective. You said the measurement, whether it's through a laser or a scope, isn't actually part of fundamental reality. So can you pick that up in general? Because it sounds not instrumentalist, but it could sound quite anti-realist in terms of, are we actually ever delving into the reality that we actually think we are doing, or is it all just anti-realist? So please pick up on that in terms of...
I don't mean to espouse anti-realism by any stretch. I am not an anti-realist. I think there's a world out there. But for me, saying that measurements done by experimental apparatuses are written into the fundamental laws of physics makes about as much sense to me as saying that armchairs are written into the fundamental laws of physics. And by the way, I don't think I'm responsible for that particular choice of word. I think someone else has said that before.
Yeah, that's a good point.
My apologies also. I occasionally get a little bit of audio distortion. If you notice any audio distortion, just let me know. Are you hearing me okay?
No, it's fine. It's fine. Always perfect. Yeah.
Just give me 1 second. I'm having a little bit of audio distortion. All right, am I coming through okay?
Continue. No, it's great. It's great. Continue.
Okay, good. So yeah, I don't mean, I'm definitely not trying to be an anti-realist. I just don't think that an experimental apparatus is a fundamental feature of reality. I'm not saying they don't exist. I think an experimental apparatus exists, but as a conglomerate of more basic features of reality. We used this word supervenience before. When I talked about Humean supervenience. I didn't define it, and I apologize. But to say that A supervenes on B is just to say that the only way A can change is if there's some change in B, and this is supposed to track the idea that B is somehow more fundamental than A, that B somehow gives rise to A in some emergent sense. And I think that experimental devices are emergent objects. They exist, but not fundamentally. I don't think things have to be fundamental to exist. If someone says, I jumped in a pond of water and came out and I'm now wet with water, I wouldn't say, no, you're not, because wetness is not a fundamental feature of reality. Things can exist without being fundamental. I think chairs can exist without being fundamental, even though defining exactly what counts as a chair is actually very hard. And I think that experiments can exist. And I also think it's very hard to define exactly what an experiment is. I just don't think that a physical theory sensibly can include experiment or measurements in the fundamental rules. And I'm definitely not the first person to say that. I mean, John Bell has a famous essay against measurement. He's pretty clear on this. But he made a very, very good point about all of this.
Yeah, just one thing there, Jake, in terms of, you know, you've been quite cautious there. Supervenience is obviously a tricky conceptual term as well in terms of properties. So there's elements in the world and they supervene on some underlying structure. So you can't change B without changing A. Are they causally related? Are they deterministically related? Do they emerge? And emergence is a tricky topic in itself.
Yes.
But supervenience obviously can be quite a contentious issue, especially when you talk about reductionism as well, in what way something reduces to something at fundamental level. So supervenience is quite an ambiguous term in general.
Yes.
And I appreciate that. Also, just one thing on anti-realism. It's always fascinates me with philosophers and physicists in terms of realism and anti-realism. So You are a realist, obviously. Most philosophers of physics and physicists are, in terms of there's an underlying structure to reality. That's something that John Worrell might call structural realism. But in
Yes.
terms of, if you look at Carl Stanford's work at San Diego, where he makes the point to me very succinctly in terms of, no, you're not denying that there's an external reality there. Hence, why would you fly? If that was the case, you wouldn't fly on a plane. So obviously, there's an underlying reality there. It's just that the theories that once depicted and represented reality, those theories are changed. And as Carl Stanford said to me as well, if you believe in the reality of scientific theories now, that means you're postulating exceptions about the present, because historically most scientific theories are now redundant. So that's very interesting. And you see that coming through where you've got people saying that space-time, that theory might be obsolete going forward. So that's one way of postulating anti-realism without thinking that there is no real underlying reality behind it. Because no, people are like, there is a structure, but those principles can change all the way through new scientific theories, but they're always an underpinning structural reality. But the theories that change over time, you've just come up with a whole host of problems with the mathematical axiom behind quantum mechanics. If we change bits of that through hidden variables, that will change bits of the theory, but it won't change the fundamental structure of reality. So anti-realism and realism is a very loaded topic for people in general.
Yeah.
But
I have very complicated views on structural realism, on naive scientific realism, on this problem of pessimistic meta-induction, that our theories keep getting replaced, and what does this tell us about whether we're converging on some approximate notion of truth? I have a lot of views on those, but that would be an entire separate interview, right?
When I discussed this briefly with you by the email in terms of necessities, I didn't mention so much about the maths. This is something I wanted to get your thoughts on. So you've already highlighted some issues and the importance the mathematics plays in something like quantum mechanics as well. So I just wanted to get your thoughts on how important, and you already alluded to, well, is this really saying something about the empirical real world? Is there actually something about observable properties? It's just an abstract element of it, and this ties into elements of philosophy of math. So my question is, simplistically, is what is the role of mathematics in the laws of physics? Are they just simply abstractions, and that's why we get problems in measurement, problems in quantum mechanics? So what is, because all physics historically and in the modern world, it's underpinned by some mathematics. So how important is mathematical logic, necessity, and abstraction when we paint it onto or use it as a tool for scientific theories? And then what are the problems with that if they're too abstract? And obviously you get problems of, like you were saying, about infinity there. So how important is mathematics for the laws of physics, and what do they say about it?
This is a really interesting question, something I've thought about quite a lot. I don't have very sharp views on this subject, but I do have some thoughts. I wouldn't describe them as rigorous arguments at this point, more just sort of impressions. I have wavered over my career in philosophy and philosophy of physics over how I think about mathematics, how I think about the relationship between mathematics and the physical world. There have been times when I was a little bit more sympathetic to the idea that mathematics had its own kind of reality. I wouldn't say that I was ever a mathematical Platonist exactly, but the idea that that mathematical truths had some kind of existence, and there was some relationship between them and physics, and given how abstract quantum mechanics is and how difficult it is to paint a picture of reality underneath the formal mathematical axioms of quantum mechanics, that maybe mathematics was in some sense prior or at least co-equal to the physical world. Now, my views have changed. I think about quantum mechanics somewhat differently. In the email exchange we had in setting up this interview, you referred to some of my recent work on quantum foundations, and that has had an impact on how I think about the kind of picture we can paint beneath the axioms of quantum mechanics. So what I would say right now is, I think I lean a little bit more toward the view that what mathematics is a very highly developed language for talking about patterns and formulating rigorous deductive arguments about structures and patterns. It's very difficult to talk in a precise, rigorous way, to formulate rigorous deductive arguments about a complicated physical theory like quantum mechanics or general relativity, or even Newtonian mechanics, I mean, really any detailed technical physical theory, it's very difficult to do that in most human languages.
Yeah, of
Most human
course.
languages are simply not adapted for that purpose.
Mm.
Human language, most human languages, English, Japanese, Spanish, they're designed to communicate thoughts and feelings, to encode memories, to tell stories, to communicate vital information about what to do, to coordinate action. And that's just scratching the surface. I mean, I'm not a linguist. A linguist would probably give you many, many, many more purposes of that language. But most human languages have not been carefully designed or adapted for capturing patterns in a rigorous way, especially
Yeah.
abstract patterns,
Mm-hmm.
and for constructing rigorous deductive arguments about those patterns. Mathematics has been designed for that purpose. So this is a little bit more along the lines of the view that mathematics is at least partially invented.
Yeah,
That
fictional account. Yeah.
it's not to, I mean, it's not to say that the patterns are not there, the structures are not there. But it is to say that what mathematics is doing is serving as a very well-adapted language for capturing and describing and making arguments about those patterns. And so mathematics has evolved over time. We've added to mathematics, we've altered mathematics to give a better and better set of tools for capturing and talking about and describing and developing deductive arguments about the patterns we see in nature. I'm not saying the patterns are invented.
No, no.
The patterns, whether you're a Humean and you think that patterns precede laws and laws are just summaries, or you're a primitivist and you think that there are some kinds of primitive laws that are generating the patterns. And again, this is coarse graining over the other views on laws that I'm not even going to mention. Either way, those patterns are just patterns. And in order to talk about them in a precise way, we have gradually developed greater and greater sets of mathematics. When we wanted to talk about shapes, the relationships between shapes, we invented geometry.
Mm.
When we wanted to talk about the relationships between quantities, we invented algebra and arithmetic. When we wanted to talk about change, we invented calculus. When we wanted to talk about electromagnetism, we invented vector calculus. When we wanted to talk about space in a more general way than we could capture, we began introducing things like differential geometry, which then became even more developed. It evolved alongside general relativity, right? A theory that really needs differential geometry, and then the two theories developed together. And this isn't to mention things like the connection between gauge theories and differential geometry, and all the developments that have happened in algebraic geometry and in category theory and all these other areas of mathematics. But there is the sense in which they've developed alongside the need to be able to talk about increasingly intricate and subtle patterns in the natural world. And I don't think that's an accident. We have patterns, we need to be able to describe them. Our language is not developed enough, and so we develop more language to do it, and that becomes more mathematics. So I do think that one can get carried away with this and begin to think that the mathematics is somehow prior to the physics.
No, no.
And this is where I begin to become a little bit nervous.
Yeah.
And although I was more sympathetic to that view earlier in my career, I've become less sympathetic to it with time. I don't know if that gets to the answer to your question about what I think is the correct relationship between mathematics and physics. But I think anytime anyone says, well, the mathematics is enough, we don't need a physical picture, I get very nervous.
Yeah, no, that's actually a point well made. So obviously, in terms of the Platonic account, that obviously numbers exist independently by themselves somewhere in an ideal form, that's not a view widely taken up these days. And I believe it's in the philosophy of mathematics. I think it's Gödel, if I'm correct, in terms of it just being an instrumental tool. And I don't mean instrumentalism, like you described it. It's a tool for describing patterns, and obviously with logical axioms, as you were saying, you can deduce statements from previous statements, so it's either in terms of truth conditions either true or false. So that works in that respect. In terms of the contemporary world, and this is why I got you to discuss it, in terms of the murky water that can happen in quantum mechanics and mathematics, when people say, oh, it's okay, it's sufficient just to have the mathematics there. No. Quantum mechanics shows why you need theories, you need concepts behind it that tie it into a wider picture. And that's obviously problematic, because if you just have the mathematics as it is, you just run into a lot of the issues that you just highlighted in terms of the axioms and the measurement problem. So that makes me nervous as well. So no, that generally answers my question in terms of the role of mathematics in theories as well. And you see a lot of contemporary physicists, I believe it's Ed Witten won the Field Medal for maths as well, as a physicist as well. But I think most physicists as well just see it as something in their tool bag. They're thinking about wider theories and how they tie into physics as well. And one of the things they can draw from, apart from theoretical considerations and conceptual analysis, is, oh, well, in my tool, here's a quick tool, here's a maths. I don't think they think the maths is sufficient as well in terms of the practice of science. And you see that obviously throughout the discussions in contemporary science in general. Talking about your papers as well on magnetic forces. And your paper is talking about the work that magnetic forces can do. And this is very interesting. So the reason this came to mind, and do forces, do powers actually do work? And this made me think of Stephen Mumford here in the UK, which in terms of the laws of physics says it's very difficult to separate a law from the causal power of that property. And someone like a human will be like, well, you don't really need to be talking about so much about their innate properties or how they govern or how they regulate. They're just a set of patterns over this mosaic. And someone like Stephen Mumford would say, well, it's very difficult to divorce their causal power from their property. So you've got a paper talking about how forces, magnetic forces actually do the work. So what is it that the work they do from these forces, and how does it relate to the causal powers possibly in these properties and laws in general?
And there's actually a couple of things, I think, lingering from the earlier part of our conversation I wanted to mention. Let me come to the magnetic forces question in just well, let me address that first, and then I'll go back to some of these other items. I don't want to get too far away from quantum mechanics, but let me say a few things about those papers that I wrote. So I wrote a collection of papers in an area that I would call classical particle physics. Mm-hmm. When we talk about particle physics, most people think about quantum mechanical particles, particle physics within the context of the Standard Model, which is formulated in terms of what's called quantum field theory, where particles are, in some rough sense, discrete quantized excitations of these delocalized systems called quantum fields. And there are various fields in the Standard Model, and they're discrete quantized energetic excitations we view as particles of various types. Photons being the particles that are discrete excitations of the electromagnetic field, Higgs bosons being the discrete excitations of the Higgs field. And then, for other kinds of particles like quarks and electrons, these are the so-called fermionic particles, the particles that they're usually regarded as the elementary constituents of matter. They're also, in some sense, the quantized excitations, but of fields of a somewhat weirder kind, fermionic fields, which are a little bit stranger. And that's all good, and we've learned a tremendous amount. And quantum field theory and the Standard Model are, fantastically predictive. They make correct predictions to many, many decimal places. They're the greatest, most empirically accurate and verified physical theories that we have. What I was interested in writing these papers was to understand how many of the features of these theories really required quantum mechanics, and how many could be understood using only the pictures we have from classical physics.
Oof, yeah.
Because anytime you can take some interesting phenomenon or feature or property of a physical theory and discover that the property still exists, even when you've simplified the theory, even when you've removed from it exotic aspects, there's a hope that you're distilling the nature of that feature or property or phenomenon a little bit better. You're sweeping away extraneous things, and you're isolating what really is responsible for this property. And maybe you could even get a clearer sense of what this property or feature is, because you can talk about it in the context of this simpler theory. So what I was interested in with these papers was writing down models of classical particle physics, classical particles, point-like entities, moving according to the rules of classical physics with none of the complications that arise from quantum mechanics, and whether some of the features we ascribe to them from quantum field theory still exist. You can still talk about them and maybe visualize them, understand them in a more clear way. So, and there's just too much to say about this. There's just too much to say about this. I'll just say a couple of things. One is there is a well-known systematic way to classify what kinds of particles can fundamentally exist by combining the rules of quantum mechanics with the symmetry features of space-time.
Mm.
And this idea that you can combine the symmetries of space-time with the rules of quantum mechanics and obtain a systematic way to classify what kinds of particles there can be. This is associated with the work of Eugene Wigner. There's Wigner again. And this is like a century old at this point. And you know, people would look at that and go, wow, isn't that a beautiful thing? That by combining quantum mechanics with the symmetries of space and time that come from special relativity, we can learn this fact about nature that we might have thought was entirely contingent, but turns out to be necessitated by these other frameworks. Well, it turns out that you get a similar classification without quantum mechanics. I'm not responsible for this. This classification was known prior to me. One of the things I do in this paper is try to simplify how that classification works and set it up in a clear parallel with Wigner's quantum mechanical version of it. So the first thing is there is this classical classification, and you can talk about what kinds of particles there can be classically. And just like in the quantum case, what you discover is that particles have a mass, or they can be massless. Mm-hmm. And particles can also have this feature called intrinsic spin, which is a form of angular momentum that is not associated with actual rotation. Our familiar experience of angular momentum is you've got a wheel spinning, and it has angular momentum, and it can transmit that angular momentum to other objects. But quantum mechanical particles have this intrinsic angular momentum that can also be transmitted to objects, can also turn into rotation of a big object. But when it's possessed by this particle, nothing appears to be actually rotating. And people often talk about spin as this intrinsically quantum mechanical feature, but it turns out that spin is a feature of classical particle physics as well. You can talk about spin, you can define it in a rigorous way, even in the classical case without quantum mechanics. Again, I'm not responsible for that either. That's an idea that predated my work, but I do think that I've clarified how spin shows up in that case. And the simple way to think about it is, just as we have the most primordial notion of energy that were introduced in Newtonian mechanics is kinetic energy. When an object is moving at a speed v, and it's got a mass m, it has an energy associated with it called kinetic energy. It's 1/2 mv squared. It's the most primeval notion of energy. It gets plugged into what's called the work energy theorem. And eventually, for some systems, you can talk about potential energy and other kinds of energy. But the most like elementary kind of energy is this motional energy, this energy associated with motion called 1/2 mv squared. And in relativity, objects can have a kind of frozen in kinetic energy, a kinetic energy that is built into the object that does not appear to be related to motion. Like a point-like particle can just have this intrinsic energy, even when it's at rest. And this energy can be converted into kinetic energy. And we call this energy rest mass. I mean, technically, it's mass times the speed of light squared, but you can think of rest mass as being a kind of frozen in kinetic energy. This sounds contradictory, but like a non-moving, a non-motional kind of kinetic energy. And once you allow yourself to think about non-motional forms of kinetic energy being mass, well, then you can talk about non-motional forms of angular momentum being spin.
Right, yeah.
To the extent that you are willing to entertain the idea that mass is a form of frozen in kinetic energy, then you are just as welcome to think of intrinsic spin as a kind of frozen in angular momentum. That's how I think about it, and that's the view that naturally emerges from this classical particle physics picture, because spin emerges from the classification in much the same way that mass does. The difference between classical spin and quantum spin is that it doesn't come in discrete quantized amounts. Classical spin can take on any continuous value, just like mass can take on any continuous value. Whereas in quantum mechanics, spin ends up only being allowed to have these sort of discrete values. So that's another part of this work. But once you can talk about this relativistic classification of particle types, and you can talk about spin as an intrinsic feature alongside mass, alongside charge, now you can start talking about other intrinsic features that classical particles can have. And these features include dipole moments. Now, there's more to say here, right? You can talk about the connection between the massive case and the massless case. When you try to take a limit of a massive particle with spin down to the massless case, you get these discrepancies. These discrepancies can be understood quantum mechanically in terms of the Higgs mechanism. And there is a classical counterpart to this. And that is a novel result that I derive in one of my papers. But I'm going to put that aside because your question was about magnetic work. So once you've got a notion of classical relativistic particles and they can have intrinsic spin and charge, you're just as free to give them intrinsic dipole moments. An intrinsic dipole moment is like giving the particle a little internal bar magnet. Now, bar magnets don't involve anything actually moving. If you get electric charges and have them move in loops, you'll produce a magnetic field. You'll produce effectively what looks like a bar magnet. That's a motional kind of magnetic dipole moment, a motional kind of magnet. But bar magnets, permanent magnets, the kinds of magnets that you just find in a rock, don't appear to involve anything moving. So we're justified in talking about intrinsic non-motional kinds of magnets. These are permanent magnets. And there's a connection between these and spin. And once you're willing to give particles, not just electric charge, but also intrinsic bar magnets, intrinsic dipole moments, you can go back to our classical theory of electromagnetism and you can ask, how does the theory have to be altered to accommodate the notion that you can have point particles that carry not just intrinsic electric charge, but also intrinsic magnetic dipole moments? And it turns out, and this is what I work on in that paper, that when you work out all the details and you write down a consistent theory, a theory in which all the forces balance, a theory that's relativistically self-consistent, a theory in which everything sort of fits together in a mathematically self-consistent way, you find that you have to modify certain aspects of the standard textbook classical theory of electromagnetism. You have to modify the law that describes how particles interact with fields, and in particular, the law by which fields exert forces on particles. And what you find is that that law is modified in just such a way that magnetic forces can exert forces. Magnetic forces can act on particles with a vector component parallel to the displacement of the particle. And this is huge. In ordinary textbook classical electromagnetism, the basic law that describes how forces operate is called the Lorentz force law.
Yeah.
And according to the Lorentz force law, magnetic forces are always perpendicular to the displacements of charges, always perpendicular. By definition, mechanical work is force dot product with displacement, with the directional motion of the thing being acted upon. You take that dot product and then you integrate that over the whole path of the particle to get a cumulative result called the net mechanical work done. And the Lorentz force law, because it says that magnetic forces are always perpendicular to displacements, means that that dot product is always zero. The dot product is picking out how much of the two vectors are parallel. And if magnetic forces are always perpendicular to the displacements, they have no component in common. They have no component that's parallel, and the work is always exactly zero. And so you'll pick up books, very good books, on introductory electromagnetism that says this means that magnetic forces cannot do work, and that is the end of the story. This is very confusing because if you pick up one bar magnet with another, if you move one bar magnet over another bar magnet, you've got one bar magnet sitting on a table, and you bring another bar magnet nearby, hovering over the first bar magnet, then the bar magnet on the table will jump off the table and stick to the bar magnet in your hand. And this isn't some esoteric experiment. This is one of the first experiments that any child does when they play with magnets. But it really does look like work is being done here. And the answer you'll get is, well, you really can't use classical electromagnetism to understand this because permanent magnets are really about intrinsic dipole moments, and intrinsic dipole moments are inherently quantum mechanical. And once you're talking about quantum mechanics, even the notion of a force becomes very blurry. And if there's no well-defined notion of a force, there certainly can't be a well-defined notion of work. So the notion of work is just inapplicable to this situation. Well, not so much, not anymore. If you modify classical electromagnetism by allowing particles to contain intrinsic dipole moments, classical intrinsic dipole moments, and you update the laws of classical electromagnetism to accommodate this, and you have a well-defined set of laws with balanced notions of forces and balanced notions of energy momentum transfer, you discover that the Lorentz force law is modified. It contains new terms, and those new terms describe a component of magnetic forces parallel to the displacements of particles that have magnetic dipole moments. And that means that there is, in fact, work being done, just as predicted. And that is also a new result, one of the results that is in this paper. And it interestingly contradicts a theorem that goes back to Niels Bohr about certain features of conglomerations of of particles and the relationship between magnetic forces and how these particles behave. Anyway, that's all discussed in the paper. Now, what does this mean in terms of causal powers?
Yeah.
I actually don't really know because so one view of what forces are doing is that forces are the causes of change. You exert a force, a net external force on an object. And here I'm speaking in classical language. You exert a net external force on an object, a push or a pull. And by net, I just mean once you've balanced all the forces, if there's any residual extra force left over pointing in some direction, that's the net force. And it's external because it's being imposed from some external source on the object in question. When there's a net external force, that's the cause. And the effect is that there is then some change in motion, the appearance of some acceleration. I think the most transparent challenge to that way of thinking about forces is Laplace's paradigm, that the way to think about classical physics is that you have at any moment in time some giant collection of objects, particles, what have you, distributed throughout the universe at some moment in time. And then what the laws are doing is they are either summarizing or governing how that conglomeration of particles should be updated at the next moment. So this is this picture that we have initial conditions, meaning a specification of all the positions and velocities of all the particles in the universe. We take those initial conditions, we plug them into a giant differential equation. Newton's second law applied to all the particles in the universe, or whatever classical equations that describe the dynamics of your system. It's some giant differential equation. And this differential equation takes the initial data and tells you the data at the next moment in time. But also, for many of these theories, because the equations are well-defined in reverse, they could also tell you the prior state as well. In this picture, there isn't a clear sense in which one object exerts a force on some other object and thereby causes it to change. So much as the entire state of the universe is acted upon in some sense by the laws of physics, which generate the next state of the universe. And then I think one could naturally ask whether causal influences are simply idle wheels. Like once I have described nature in terms of some state of the entire universe being propagated forward or backward by a giant differential equation, what more is added by trying to introduce the language of cause and effect? Well, certainly if you want to summarize what's going on to somebody and you say, well, it looks like, your knee hurts. Your knee hurts because a rock fell off this hill and bumped into your knee. That's a causal story. The rock rolled off the hill and caused the pain in your knee. And we use causal stories simply so that we can communicate with each other. But the causal story really is some emergent thing supervening on this deeper microphysical picture in which causation doesn't exist.
So obviously this is Bertrand Russell's obviously very noted in this space.
I was going to mention exactly the Bertrand Russell, right? That he said that causation is like the royal monarchy; it continues to exist merely because people mistakenly think it does no harm.
And obviously, as you alluded to there in terms of the system, because equations that you can run in reverse in terms of what goes forward can also go backwards. Obviously, in terms of the temporal asymmetry is a problem for causation, hence why Bertrand Russell had the whole issue of, well, we should take causation out of modern physics for reasons you alluded to. Continue, sorry, Jacob.
So, but the upshot of all this is that in light of this Laplacian or Russellian picture in which cause and effect are at best emergent conveniences that we use to communicate with each other and not to be found in the microphysics, in the detailed rules and behavior of the fundamental constituents of reality. I don't think there's necessarily an obvious sense in which magnetic forces doing work are exerting causal powers. You can't say causal without cause and effect, and I'm not sure that causation in the classical sense has a place there. Okay, but this is actually a very good segue back to quantum mechanics, interestingly enough. So one view to take from all of this is that perhaps causation is at best an emergent feature. Maybe it's not really there at all in any sense. Maybe it's fictional. It's It's as John Norton, the philosopher of science at University of Pittsburgh, has described it, as a form of folk science.
Yeah.
That we don't need it, we should get rid of it. And that to the extent that we ever use it, it's just for convenience and isn't really part of what we're trying to do in science. I think that's one view. Another view is that just because it's immersion doesn't mean it's real. Just like wetness, we're not going to say you're not wet, or we're not going to say there aren't chairs. Things can exist without being fundamental. That's another view. That I would say that means that you're not a causal eliminativist, but you're an emergentist about causation.
Yeah.
But this has bothered me for a long time.
Yeah.
Whenever I go to a seminar on quantum mechanics and quantum foundations, and someone starts talking about, oh, local causality, or they start talking about interpretations of quantum mechanics that entail retrocausality, or they use the word causal, I do not know what they mean.
Yeah.
And I don't mean this in a glib way. I'm not trying to be contrarian here. I literally am confused about what the word is that they're using. They seem to know what they mean by it, but whenever I ask, what exactly do you mean by causation here? They don't really have a well-defined sense. They have an intuition about it, but human intuition is not the place to look when you're trying to understand fundamental physics. This has been in my head for years. Let me now get back to the project I'm working on about quantum mechanics, and I'll explain why this is connected to causation. So I said that I'm now very sympathetic to option 2 in dealing with the fundamental problems of quantum mechanics as exemplified by the Wigner's friend thought experiment, the idea that somehow the wave function or density matrix cannot be complete. I would go one step more. I don't think the wave function exists.
And this is very interesting. First of all, explain that and why that's important, and then that gets into this. So if it doesn't actually exist, what is it doing in terms of the scientific?
Good. So Max Born of the Born rule, Nobel Prize winning physicist, one of the creators of matrix mechanics, which became quantum mechanics, luminary figure. He wrote a beautiful memoir that I highly recommend called My Life, Recollections of a Nobel Laureate. It is one of the best history books on physics I've ever read. And it's written from the first person perspective of someone who lived through these experiences and knew all these characters. What's fascinating about it, and this is just a little bit sociological now, is very little of his personality comes through in this book. And I've never heard anyone describe Max Born's personality, anybody. He appears to have been as lacking in a distinctive personality as you could imagine. But he was an extremely good observer of other people, which I think is appropriate for someone who worked on quantum mechanics, being a good observer. Right? He was a very, very good observer, and he had a great memory, and so he describes all the other personalities in incredibly rich, colorful detail. I learned so much about all the other characters. I have a much better sense about what Wolfgang Pauli was like, what Einstein was like, what Schrodinger was like, what Heisenberg was like, what all these people were like from, Max Born's description. And the stories are incredible. His stories about David Hilbert, his stories about Oppenheimer, it's extremely interesting. So I highly recommend it. So he says in the memoir, when Einstein asserted that the luminiferous ether did not exist, it was a big deal. Since, centuries ago, right? I mean, there was a long-running dispute about what the fundamental nature of light was. There was the corpuscular theory of light, that light was made of a stream of classical particles of very low mass moving around. There was the theory that light was ultimately wave-like. The Young double-slit experiment indicated that light had clearly wave-like properties, that it exhibited interference effects. And so this picture that light was a wave-like phenomenon took over, became the dominant view. But if you have a wave, the question is, what is it a wave of? Right? When you look at a water wave, you look at an object, something that looks like a feature of the water that travels from one place to another. But if you look at what's actually happening, right, all you're seeing is that little pieces of water fluid are just moving up and down. They're not really moving from side to side. They're moving up and down. And there's this emergent effect of what looks like a thing that's propagating at some speed. All the waves we know about, whether water waves or sound waves, the wave is not its own autonomous piece of the ontology. It is the emergent effect of some underlying medium, some substance that is just oscillating or going up and down. And what we interpret as the wave is just the sort of emergent effect. So the natural question was, if there are waves, if light is made of waves, then there's some substance that's oscillating or moving up and down. And this light-bearing heavenly substance, literally luminiferous ether, is really what electromagnetism is about. That's the ontology underlying electromagnetism. It's some kind of ether substance filling all of space. And what we think of as electric fields and magnetic fields and waves are really depressions and oscillations in this ether. And Max Born wrote that by the end of the 19th century, people were so convinced of the existence of ether that, as he put it, physicists believed that they had a more precise understanding of the material properties of ether than they did of the material properties of material, of matter, of physical matter. That's how convinced they were that ether was a physical thing. Because without ether, how could you possibly explain what was going on? How could you explain all these features of light, the fact that light exhibits stresses and momenta and all these features?
Similar to biases in biology.
Right. And Einstein says, no, there's no ether. And without ether, he's able to simplify the theory significantly. He's able to introduce special relativity and all these famous experiments, some that are more well-known, like the Michelson-Morley experiment, where they measured the speed of light in different directions as Earth was moving through the ether and discovered that the speed of light was the same no matter how Earth was moving through it, which is very difficult to understand in terms of ether. And then the Fizeau experiment, which was less well-known. And there are many experiments that made it very difficult to handle the notion of ether. And now all of a sudden they go away. Without ether, everything simplifies, and you get a much simpler theory, and you get the dawn of special relativity. Isn't that very nice? What I'm arguing is that wave functions, and more broadly density matrices, are the ether of the 20th century. They don't really exist, just the way that the ether didn't exist. And just as people used to think that electromagnetism was fundamentally about the ether, to the extent that people like Maxwell and Lord Kelvin were trying to argue that matter was itself a manifestation of the ether, that these topologically stable solutions to the differential equations that we use to describe the ether fluid, these knotted solutions, were atoms, and all matter was actually made out of the ether. That's how seriously they took ether as the fundamental substance. Quantum mechanics has long been believed to be about wave functions or density matrices, that they are the ether, the material that underlies quantum mechanics. And what I'm saying is that's false, that we have no good reason to think that there's historical reasons why we ended up in that place, but that the proper way to think about quantum mechanics is not that it starts with, okay, there's a wave function, here's what it does. Axiom 1 is already off in the wrong direction. To say that the quantum system is properly represented by a state vector or wave function, or more broadly, a density matrix in Hilbert space, I'm not saying it's wrong as a piece of a predictive empirical prescription. No. I'm just saying it's wrong as a statement of the ontology. That's not what fundamentally exists.
That's perfect. So that goes to say, obviously, no one argues for the exact same reason you just mentioned in terms of its prediction. Obviously, you've got quantum computing these days. Historically, in the lab, it's spectacular in terms of its results and predictions. It's been proven time and time again empirically in terms of predictability in the lab to be correct. Obviously, Roger Penrose wouldn't deny the predictability in the lab either. But in terms of exactly what you're saying there, the fundamental ontology, is that actually really picturing reality? Probably not. So are you saying that there's something where the wave function is the ether of the contemporary world? Are you saying there's something more fundamental than the wave function?
Exactly what I'm saying. Exactly. So, and at some level, this shouldn't come as a shock.
Yeah.
When Schrodinger first introduced the wave function in late 1925, early 1926, in his theory of undulatory mechanics, which is now called wave mechanics, he was the first person to introduce the wave function. For him, the wave function was not an abstract vector in a Hilbert space quite yet. That didn't come yet. For him, the wave function was what we would call its position space representation. You take this abstract state vector. Schrodinger didn't have this yet, but effectively this is what he was doing. You take this abstract vector in this Hilbert space, you pick a basis that corresponds to position measurements, and you can express the wave function as a collection of numbers or amplitudes. And this collection of numbers associated with different possible positions becomes a function, and that's the wave function. When you're dealing with a wave function of a single particle, the wave function is a function whose domain, where the wave function lives, looks like three-dimensional physical space. And this leads to a very naive picture that every particle has this wave in three-dimensional space moving along with the particle. This picture is wrong. Wave functions do not live in physical space. Schrodinger knew this immediately. In those early papers, he pointed out that as soon as you have two particles have a six-dimensional configuration space. The configuration space is the set of numbers that you need to identify classical arrangements of the particles. You need three numbers for the first particle and three numbers for the second particle. XYZ for the first particle and another XYZ for the second particle. It's a six-dimensional configuration space. And that's the domain of the two-particle wave function. It's a function that lives in configuration space. If you have n particles, it lives in three n-dimensional space. Schrodinger knew this. He talked about it in the paper. And this is one of the things that Einstein and Heisenberg agreed on. Einstein and Heisenberg did not agree on a lot of things. But they both agreed that it was preposterous to think that there were physical objects in three n-dimensional configuration space, and that this was the ontology of reality. In fact, the famous quotation where Einstein writes in this letter to Max Born that he doesn't believe that God played dice with the universe, the very next sentence, which is usually not included, is Einstein saying, waves in three n-dimensional space, oscillating as if connected by rubber bands or something. I mean, he thinks it's preposterous, and he writes several letters to other people, to Lorentz and various other colleagues, talking about how he just can't take seriously the idea that the seat of reality is some high-dimensional abstract configuration space. And then what happens? Schrodinger eventually recants this view, and by 1928 is saying in his lectures that he doesn't think anymore that the wave function is physical ontology and configuration space. This view has persisted. It's now called wave function realism, the idea that a wave function as a function in configuration space is somehow the seat of ontology. And this is a view that a number of people have expressed. I'm not going to name names. Another view is that, no, we have to abstract from this particular position space representation and talk about state vectors, the vector in the Hilbert space, not configuration space anymore, but the Hilbert space. And maybe a vector or a density matrix in a Hilbert space, maybe that's the ontology. But that's not any better. I mean,
exactly.
I don't think Hilbert space is a better seat for ontology than configuration space was. It would take a lot of convincing to persuade, I think, a lot of people, including me, that what nature fundamentally is a ray, an equivalence class of state vectors, or a density operator living in a high or infinite dimensional vector space over the complex numbers twirling around according to some unitary law. And that's what nature fundamentally is. It's not that it's impossible. We can't prove it's impossible, but the bar is high. That's really what's going on.
Sorry, Jacob, just very quick. That just goes to show, obviously, what we were discussing earlier in terms of the limits of mathematics and abstraction and how they imply to an underlying reality as well, which that highlights the point there. For example, is the Hilbert space actually reality in a law? You just said it's a very high bar. As an example, continue.
Right. This is a form of Hilbert space realism or state vector or density matrix realism. And, to me, this is exactly making that mistake we talked about before, and that you're just highlighting right now, of taking mathematics to be primary to physics. Because the Hilbert space is certainly a mathematical thing.
Of course.
And we're saying that reality somehow emerges from pure mathematics. Now, people will say, no, that's not what I mean. Really, I mean that nature is physical, but the only way to talk about that physical thing that nature is to describe it using Hilbert spaces. But to me, that's a distinction without a difference. If the only way to capture a physical thing is purely through an isomorphism to some mathematical structure, then you're basically saying that it's pure mathematics. Okay. So what some people will do is they'll say, well, maybe we should supplement quantum mechanics with hidden variables, with extra information. I mentioned that was option 2, where you have some uncollapsed density matrix, but you still have a unique outcome at the end of the experiment. And so those things are called hidden variables. Now, there are folks like Tim Maudlin who says that hidden variables, that's not a good term for it, because in fact, what you really see in the experiment is the hidden variables. You don't see the wave function. You see the positions, you see the recordings, you see the measurements. We shouldn't call them hidden variables. We should call them additional variables. Now, the reason why they were called hidden variables was because you have quantum mechanics which makes probabilistic predictions, and the idea was maybe we're only making these probabilistic predictions because at a deeper level of reality that we can't see right now, there are in fact lots of moving variables or particles or something like that, and they're giving rise to the probabilities in a way similar to how statistical mechanics can give rise to thermodynamics. And so they're hidden in the sense that they're going on behind the scenes and giving rise to these probabilistic predictions. But what Tim Malden, I think, rightly points out is, well, but these are indeed the things you see. They're not really hidden variables. They're additional variables. But I would actually disagree with him there as well. They're only additional variables if they're in addition to something else, the wave function. And I don't accept that the wave function exists.
That's a problem.
So I would not call them additional variables either. I would just call them the ontic variables. That's it, right? The variables that represent the ontology directly. And that's it. And so the question you can ask now is, if you banish the wave function, just like we banished the ether, and you just say, what can we get by with just talking about the ontic variables directly? Which ontic variables? Depends on the system, just like classically. If you're talking about a system of particles, the ontic variables are the arrangements of the particles in space. If you're talking about a field, then you're talking about field intensities in some delocalized sense across space. If you're talking about strings in string theory, then you're talking about the arrangements or configurations of strings. There isn't one answer here. Just like classically, there are different kinds of classical systems with different kinds of ontology. There are different kinds of quantum systems, and arguably they have different kinds of ontology. Maybe we'll discover a fundamental unified quantum theory in which we identify the true ontology underlying everything, but we don't have that yet. What we have is a bunch of different quantum theories, and each of them are modeled in different ways, and they can be given different ontologies, just like we would do it classically. So when someone asks me, what am I saying the true ontic variables are? It's model dependent. It depends on which model you're considering. And again, one day we may find a unified model that underlies everything, on which everything supervenes. Until then, we have different ontic variables for different models. And the next question is, okay, well, these ontic variables, these are the things we see. We see arrangements of particles. We see intensities of fields, maybe indirectly through the behaviors of particles. But nonetheless, we have all these ontic variables. Can we write down laws for these ontic variables so that we get the same empirical predictions as quantum theory? That's the question. And this gets to a question that you asked me over email before we had our meeting. In what sense, how do laws work in this picture? Are we saying the laws are prior to, and the answer is, I don't exactly know whether we should think about these laws in a Humean way or in a primitivist way. But there's just a question. If I've got ontic variables, can I write down laws that will give me a theory that makes the same predictions as textbook quantum theory, but without a measurement problem, without any preferred role for measurements? But more than that, a theory in which instead of only being able to talk about measurement outcomes narrowly, we can talk now about phenomena really happening. So if you think about it, there's something else that's very weird about textbook quantum mechanics. The only phenomena it describes are measurement outcomes. And that either means that there are no other phenomena happening in nature, which seems a little bit surprising, that only measurements are happening, or it means that all things that happen are in some sense measurements. But then if everything is a measurement, then that makes the measurement problem even worse, because, well, then if everything is a measurement, then why isn't everything it becomes a mess? You know, or that other things happen, but that quantum theory simply is incapable of telling us what those things are.
It also, one thing there that Jacob, doesn't it also blur the line even more problematically between a law and the theory? It's hard to separate that in that respect as well.
It just becomes a mess. In this picture, we're not just talking about measurements happening. We're talking about ontic variables representing things that are really happening in nature, phenomena really happening. So when birds go foraging, it's because the particles or fields or ontic variables that they're made up of are actually doing things out in nature. When people fall in love, it's because actual things are happening physically in nature. When early universe plasmas are mixing, it's because actual stuff is really doing stuff. You don't need to rely on measurement to be able to talk about phenomena taking place. I call this, by the way, the category problem, that you have this narrow category of measurements alone, measurement outcomes alone, and this much broader category of phenomena happening, and how do we traverse the gap between these two things? What people will often say in the textbooks is, oh, you just have to take averages of measurement outcomes, and that gives you phenomena happening. But an average of measurement outcomes is still just measurement outcomes. It doesn't take you from the category of measurement outcomes to the broader category of phenomena taking place.
Exactly.
This new picture that I'm describing does, because it's stuff actually happening. And then some of that stuff that happens will be a measurement, just like some of that stuff happening will be a chair sitting on the floor of your room. And it demotes measurements to just one more kind of a thing that can happen, rather than giving it a starring role in the theory. But this would all be doomed if we either could not come up with a good set of such laws that take these ontic variables and replicate empirically the predictions of quantum mechanics, or if we could come up with the laws, but the laws were so complicated, so fine-tuned, so messy, so difficult to formulate, and to borrow an American a term here, so gerrymandered,
Yeah.
carefully designed just to give you the right results, as if you're fitting it to a curve, that they're just not compelling, that they seem contrived and artificial. That's the problem. Now, in the early development of quantum theory, from 1900 to about 1923, 1924, people were looking for these laws. They had a picture of particles going in orbits around atoms. They had a picture of ontic variables, but they couldn't come up with a set of laws that would give the correct results. So they abandoned that picture and, on the one hand, embraced pure abstraction, matrix mechanics, or wave functions, Schrodinger's wave function approach, his undulatory mechanics, and eventually a synthesis of the two into Hilbert space, Dirac von Neumann axiomatic quantum mechanics, which abandoned the pictures altogether, abandoned these ontic variables altogether. The claim I'm making is that this was premature, that if people had sat a little bit longer and thought a little bit more flexibly about the form laws could take, they could in fact come up with laws that are relatively simple and compelling, that when acting on these ontic variables replicate the predictions of quantum mechanics. And in some sense, that's all I've done. I've come up with a set of laws that when acting on these ontic variables give you the same predictions as textbook quantum mechanics. These laws are a little bit more general than the kinds of laws we're familiar with. They are not deterministic. This picture resembles in some ways the hidden variables approach of de Broglie and Bohm, now often called the de Broglie-Bohm theory or Bohmian mechanics, named after Louis de Broglie and David Bohm, who independently developed it and eventually synthesized it together. In that picture, you have additional variables. You also have a wave function. The wave function is either ontological in some views or a little bit less ontological and more like a law. That's more along the lines of folks like Shelley Goldstein and Nino Zangi and people who think of it that way, the nomological Bohmian approach. And you have all these steps. You first have to, you have initial conditions in the wave function, you have to solve the Schrodinger equation, and once you have the wave function, it then goes into another equation called the guiding equation, and that guiding equation deterministically guides the path of your ontic variables, particles, essentially. So it's this multi-step process. First, you find the wave function, and then you insert that, and it behaves as a so-called piloting wave that through the guiding equation pilots the particles around. The problem with Bohmian mechanics, one of many, many problems, it's got many, many problems. It's never been successfully generalized beyond very simple systems. It really seems to have helped itself to many distinctive features of the case of finitely many non-relativistic quantum mechanical particles, fixed numbers of finitely many non-relativistic quantum mechanical particles. And has proved very, very difficult to generalize more broadly. That's one major problem with it. It's also very unwieldy. It's got this pilot wave going around. It's very complicated. It does hang on to a deterministic picture in the sense that the Schrodinger equation for the wave function is a deterministic equation. Given initial conditions, you get a unique answer. Then the wave function gets plugged into this guiding equation, which acts deterministically on the particles, tells you definitively where they will go. And the probabilities of quantum mechanics come from uncertainties or assumptions about the initial probability distribution over the initial conditions of the ontic variables of the particles getting transmuted into probabilities for where the particles will go. That's how the Bohmian picture works, but it's very limited. I found the Bohmian picture very limited. In this picture, my picture, which you could think of as, it's got a couple of names, and maybe I'll explain the names in a moment. But in this picture, we banish the wave function. There is no wave function, at least not in any fundamental way. You can derive a wave function later on as a useful piece of mathematics, and it is very useful, but it doesn't play a primary role in the theory. It's not one of the starting assumptions of the theory. It comes later if you need it. Instead, you've got these ontic variables. There's no piloting, there's no guiding equation, and none of the consequences that come from a guiding equation, like picking out a preferred Lorentz frame, which is in tension with special. None of that happens. It's all not there. You just have these ontic variables, and you just directly have stochastic laws. So deterministic laws are laws that take some initial information and tell you uniquely how the system will end up or how it will evolve without the use of probability. Stochastic laws are laws in which probability is baked into the laws.
Mm-hmm.
The laws don't tell you exactly where the system will end up, even given a knowledge of the initial conditions, even given a perfect knowledge of the initial conditions. Instead, the laws fundamentally only tell you a probability distribution of where the system will end up. Those are called stochastic laws. And you might think, well, this is kind of obvious. Quantum mechanics makes probabilistic predictions. Why didn't anyone think to just look for probabilistic or stochastic laws acting directly on particles or fields or whatever, and just never have to worry about wave functions? Why wasn't this done before? It was. It was attempted several times. The earliest well-defined such picture that I know of was by Bopp, B-O-P-P, in the 1940s. His work was actually mentioned in Everett's long-form dissertation on the theory of the universal wave function. Everett points this out and says this is a rival way to do it, a rival approach to quantum mechanics. This is picked up by Imre Feniers in the 50s, and most famously by Edward Nelson in the 60s, and is now called Nelsonian stochastic mechanics. Mm. It turns out to still be extremely complicated, and it looks very gerrymandered. It begins like Bohmian mechanics by positing a wave function and solving the Schrodinger equation. And then the Schrodinger equation is plugged not into a deterministic equation, but it's plugged into a stochastic differential equation that makes probabilistic predictions about how the particles will move. And these stochastic differential equations turn out to be extremely complicated, very gerrymandered, meaning that they are carefully designed, like after the fact, like as a curve fitting exercise to match the predictions of quantum mechanics. So they look very unnatural. They have lots of ad hoc parts to them. They're very difficult to motivate, except because you know what answer you want to get. They just don't work very well. And like Bohmian mechanics, they ended up not generalizing very neatly to more general systems. I should say, by the way, that when Bohmian mechanics when there have been attempts to generalize Bohmian mechanics to like quantum fields or more modern physical theories, those also often bring in stochastic laws. So there does appear to be some difficulty in having a purely deterministic picture when you try to generalize from the case of a fixed number of finitely many non-relativistic particles, whether you're trying to do Bohmian mechanics or anything.
Just in terms of the stochastic laws, is obviously it's not deterministic, and some people say that well, if it's not deterministic, then how can it be a law? But it's something I was discussing with Barry Lowe as well, in terms of at some point a stochastic law gives you a probability, and that's going to be a law ultimately, because even though it's in a probability range, it can't be outside of a probability range. So in that respect, it's probability law. Continue.
You're completely right. And this is where thinking about laws a little more flexibly really came in handy.
Yeah.
If you take a primitivist view on laws, you might, now this isn't to say that you have to, by no means do you have to, but it does sometimes give people the inclination of saying, well, laws can only be like this. Laws can only be deterministic. If the law is not deterministic, it's not a law. Whereas a Humean would say, a law is any useful way to summarize the mosaic. Right? If there are patterns, and the simplest, most compelling, most explanatory way to summarize those patterns is using stochastic laws or probabilities, that's just as good a law as any.
Yeah.
And then, of course, you go back to the primitivist and you say to the primitivist, why can't laws be probabilistic? Who says they can't be? And then you realize, but thinking about laws more flexibly was helpful for me in this. So you're completely correct. So the question is, what changed? Why do the stochastic laws in the picture I'm describing seem to work, whereas the older stochastic approaches did not work so well and have mostly been abandoned? And the answer is, there was a crucial assumption made in those earlier stochastic approaches. This assumption is known as the Markov assumption, Markovianity, also known as memorylessness, which is the statement that not only are sure, we can let the laws be stochastic, but we're going to retain the idea that laws are dynamically productive. You take just the current state of the universe, and then you apply the laws to it, and you get the next states of the universe. And now we're granting that the predictions are probabilistic, but they're still in this paradigm that you have to have the current state, and then it tells you the later states. There is no good reason for this. There's no good reason for this. It just so happens that Newtonian mechanics works that way. And Markov chains, which are widely used in statistics and probability and modeling, work that way. But in all those modeling exercises, the Markov assumption is made as an idealization. There's an awareness that probably it doesn't exactly hold. It's just convenient. It's a convenient approximation. If you drop that approximation, if you allow your probabilistic laws, your stochastic laws, to be non-Markovian, then you can write down extremely simple laws that replicate the exact predictions of quantum mechanics. And this appears to be the missing step. It appears to be the thing that people couldn't see. It's like, you know, well, I mean, it's like other historical examples of people overlooking an assumption that seems so intuitive that they couldn't imagine they couldn't imagine, they couldn't even see that they were making it. When you drop that assumption and allow your stochastic probabilistic laws to be non-Markovian, there are very simple laws you can write down, as simple as the laws of textbook quantum theory that replicate the predictions of textbook quantum theory.
Thank you.
This lack of Markovianity is a form of a lack of an ability to divide the laws across time. When you have Markovian laws, or you have laws like Newtonian mechanics, which in some sense are a trivial version of the Markovian laws, if you want to evolve a system from one time to another, you can evolve it in one go, or you can break the time up into smaller parts and evolve it in steps, and your laws are rich enough to tell you what happens over each individual step. This is called divisibility.
Yeah.
The laws that I'm describing do not have this feature. They're indivisible. So you could call this indivisible quantum theory without wave functions, where you just have indivisibly stochastic laws. And there's a precise correspondence between this picture and textbook quantum theory that I call the stochastic quantum correspondence. So you can call this larger project the stochastic quantum correspondence, or you could just say that we're replacing textbook quantum theory with this indivisibly stochastic theory, this indivisible version of quantum theory, with ontic variables that are evolving according to indivisibly stochastic laws. And that's it. There's a lot of technicalities that I'm not going to get into, because for that you can look at the paper, but that's the basic notion of the idea. And as far as I know, nobody had this idea, which is to me astonishing. It's a relatively simple idea, but it just wasn't noticed all this time.
Okay.
Now, well, end up is your question about causation, because this is where we finally reconnect with causation. Indivisible stochastic laws turn out to give a really beautiful way to talk about causation. So I said before that I had become very skeptical of the idea that causation had a fundamental existence at the level of microphysics. That's true in Newtonian mechanics. In Newtonian mechanics, you have deterministic time-reversible laws at the level of the microphysics. And then you have all these questions about how could you have cause and effect when the future and the past, have the same microphysics? Where you get the asymmetry from? There appears to be fundamental obstructions to trying to locate or situate causation at the level of the microphysics in something like Newtonian mechanics. But in these indivisibly stochastic theories, that goes away. There are, in fact, beautiful ways to talk about causal relationships and causal influences using this different set of laws. I cannot possibly do justice to this conversation right now, but I'll just say that I have another paper where I take these new microphysical laws, these new indivisibly stochastic microphysical laws, and I show that there is a very natural way to talk about them in causal terms, to situate notions of causal influence directly in terms of them, then to take that notion of causal influence and go back and address longstanding questions about causation and local causation in quantum mechanics, including challenging some folk wisdom about how local causation is supposed to work in quantum mechanics. So this is what I'm working on right now, and this is why I'm very excited about this stuff. Without wave functions in the ontology, there is no entanglement in the ontology. And with that entanglement in the ontology, the threat to Humean supervenience evaporates. And I think that's an important, so it's not that entanglement doesn't show up in this picture. It does. It shows up at the level of probabilistic behavior. You get the same predictions as you would get if you treated entanglement ontologically. But in this picture, the wave function is not ontological. Entanglement is not ontological. You, in fact, go back to a picture of phenomena taking place in something like space. And you go back to being able, if you wish, to taking Humean supervenience seriously. This is not a compelling argument that you must, but it reopens that up as a possibility. Perfect. That's the sense in which I mean that this new picture makes the world safe for Humean supervenience for those who prefer it.